Okay, so from now on, we're gonna embark on the study of magnetostatics. And this is the field where one considers the behavior of magnetic field due to a steady current, steady state current. And let me begin by emphasizing the obvious fact that the only way to generate the magnetic field in the framework of classical electromagnetism is the current. I take it back. The only way to generate the magnetic field in the context of magnetostatics is the current. Okay? And that's manifest uh, in this equation, which is one of the Maxwell's equations in the presence of state. In the case of steady state, so in the steady state, any sort of time derivative will become zero, and in that circumstance, the curl of the magnetic field is proportional to the local current density vector, while the divergence of the magnetic field is strictly zero. So what this is telling us is that if you want to generate the magnetic field, then you must have an electric current somewhere in space. Now, when you learn quantum mechanics, or if you have already learned quantum mechanics, you will find out, or already have found out, that there's this new thing called the electron spin, or the proton spin, or the spin of any elementary particle, which also acts as the source of magnetic field. So you don't necessarily have to have a moving charge in order to generate the magnetic field. But since we don't have anything to represent the spin degrees of freedom in the classical electromagnetism, we can confidently say that in a steady state situation, the only way to generate magnetic field is by having some electric current. Okay, one very simple consequence of these relation is that once you take the divergence of the left-hand side, then by virtue of the vector identity, this becomes zero, which means that the divergence of the right-hand side is also zero. So it's divergence. It's a divergence-free condition, and of course we're very familiar with this relation, because this is a kind of relation that obtains when you have the time independence in the continuity equation. So what that implies is that in the situation for magnetostatics, only the steady state current is allowed. But of course, when you think about it, that's kind of self-evident, because if there was time dependence in the current density, and at the same time you say that the current density is the source of the magnetic field, if the source is time dependent, then the result, namely the magnetic field, will also be time dependent. So that was a self-evident statement in hindsight. Now, the other interesting consequence of the magnetostatics equation is that the divergence of the magnetic field is zero. And this is not only true for the static situation, where time dependence is absent by assumption, but this is true for even the dynamical situation, where you have all sort of temporal fluctuations of charges and current and whatnot. So this is a rather powerful condition on the behavior of the magnetic field. And even when you go to the quantum mechanical formulation, this relation still does not change. So this is probably one of the most powerful constraints that exist in the laws of the universe. That the divergence of the magnetic field is strictly zero in all space at all times. And as a consequence, the volume integral of the divergence is zero, which means that the flux through the closed surface of the magnetic field is always zero. Now, pictorially, there is there's a pretty simple pictorial way to represent this condition that there can be no flux, no net flux through the closed surface. So having no net flux implies that if a certain amount of magnetic flux enters a certain portion of the surface, then exactly the same amount of flux must also leave through the other side of the surface. And that means that the magnetic field line either has to just pass through the surface or it would have to form some closed loop like this. Okay, so these are the only allowable situations for the magnetic field lines that are consistent with this powerful constraint of having no divergence whatsoever. Okay, so the other interesting factoid about magnetostatics is something known as the Thomson's theorem. So this Thomson is the same guy as the Lord Kelvin. So Thomson is someone who did all kinds of things in all kinds of fields, including the field of electrodynamics. Of course, he also made important contributions in thermodynamics and also engineering. And he was a pretty versatile guy. And there are a couple of theorems in both electrostatics, electromagnetism, and also in fluid dynamics that bear his name, which probably means that he was very good at mathematics of his day. So let's remember we proved something called the Earnshaw's theorem in electrostatics. And what the theorem stated was that in free space, where you don't have any charge, the electrostatic potential can neither be a local maximum or a local minimum. Okay, so analogous statement for magnetostatics is known as Thomson's theorem, one of Thomson's many theorems, I should say. So to prove this so-called Thomson's theorem in magnetostatics, I'm just first walk you guys through the derivation, and at the end of the derivation, I will simply state the content of the theorem. Because once you have familiarized yourselves with the steps of the derivation, then the statement of the theorem will be more or less evident. So what you need to consider to prove Thomson's theorem is to consider this flux of the gradient of the magnetic field squared. So this you might call the magnetic field density or magnetic field density squared or whatever. You take the gradient of this magnetic field density and try to measure the flux of that gradient through some closed surface. Okay, that's the beginning of the derivation. And when you see such an expression, you can invoke the Gauss theorem, of course, to convert the surface integral to a volume integral. And the integration element is the Laplacian of the magnetic field density. Okay, so far it's not at all clear where this is going, but let's have a little bit of patience and just push along with the calculation. So this Laplacian of the B field squared, when you write it out as components, is like this, and then this becomes that. I just act with this derivative, and since this is acting on something square, you have a factor 2, which is natural. So as with the Earnshaw's theorem, we're going to think about the region which is free. So the free region is the region where you don't have any charge and you don't have any current. So in the current free region, the curl of the magnetic field is also 0. So now that means that this indices can be interchanged, right? Because if you take the difference of the two, then that's just one particular component of the curl. And in free space, that curl is 0. So you can freely interchange the two indices as shown here. Okay, so by virtue of this identity, you can replace this derivative del I bj by del j bi. Okay, then this expression equals the sum of this part and this part. But this the second part, after a little bit of manipulation, becomes 0 because it ends up being some sort of derivative acting on the divergence of the magnetic field. But we already showed that the divergence of the magnetic field is strictly 0 under all circumstances. So now we have only this expression left over. And once again, if I see a del jbi, I can just replace it by del ibj. And then this whole thing becomes del ibj squared. So now we're almost at the end of our derivation. So we started out with an expression which is some sort of flux of the magnetic field density. And we managed to prove that this flux value is equal to the volume integral of this thing squared. But since we are integrating something which is a square, then the result has to be greater than 0, or at least certainly cannot be allowed to be negative. Okay, now what that means is that it's possible to have a configuration in which this gradient have directions that are entirely flowing out of the closed surface, but certainly not entirely flowing in. You might have situations where some of these arrows are flowing in and other arrows are flowing out, so as to maintain the 0 for this integral. But certainly it's not possible to have all the vectors flowing in, because then that would violate this condition that this integral be non-negative. So here's the statement of Thomson's theorem in magnetostatics. What Thomson's theorem states is that in magnetostatics, in free space where there's no current density, you can have a local maximum of the magnetic field, uh, which is quite different from Earnshaw's theorem, saying that you cannot have a local maximum of the electrostatic potential. But it's still impossible to have a situation where the magnetic field size is a local minimum. That would violate this inequality that we just derived. Okay, so if you're someone designing a new sort of magnetic device, no matter how clever you try to be, there's no way you can go around this theorem and try to defeat it and come up with a device that will create a local minimum of the magnetic field density. That's just not possible in the framework of the laws of electromagnetism.